We continue our discussion on the cutting stock problem. We were looking at this problem of cutting 511 sheets of 9 inch, 301 sheets of 8 inch, 263 of 7 inch and 383 of 6 inch from 20 inch sheets. We also defined xj as the number of sheets which are cut using a pattern j, and the problem reduced to one of minimizing the total number of sheets that are being cut. We also formulated this problem of this type by making this as an equation by considering an exhaustive set of patterns where the waste can even be more than 6. Now, we started the solution by considering this basis, which means by considering patterns that use only 9, only 8 inch, only 7 inch and only 6 inch. And we said if we follow these 4 patterns, then we would require 255.5 of the first pattern, so much of the second, third and fourth, which gave us 665.16 sheets. Next thing that we had to do is to find out whether this is optimal. Now, in order to find out whether this is optimal, since the problem is a minimization problem, any negative, strictly negative Cj minus Zj can enter the basis. So, Cj if there is a pattern j such that Cj minus Zj is less than 0, then such a pattern can enter the basis. Now, this reduced to saying that if there is a pattern j such that ypj is greater than 1, then such a pattern can enter. Now, y is the solution of the dual associated with this solution. So, y was computed as 1 by 2, 1 by 2, 1 by 2 and 1 by 3. Now, any feasible pattern should satisfy the condition 9a plus 8b plus 7c plus 6d less than or equal to 20, where a, b, c and d are the number of 9 inch, 8 inch, 7 and 6 that are cut out of a given 20 sheet. So, this constraint has to be satisfied by every feasible pattern, and if a feasible pattern satisfies this condition, that half a plus half b plus half c plus 1 by 3 d is greater than 1 and a, b, c, d greater than or equal to 0 and integer, then such a pattern can enter the basis. Now, what we did was we also used some ideas from a single constrained knapsack problem. We also said that because this is a strict greater than or equal to type inequality, we said we would now make this as the objective function and write this problem to find a, b, c, d such that it maximizes this function subject to this constraint greater than or equal to 0 and integer. We also borrowed some ideas from a single constrained knapsack LP relaxed version of such a problem and said that if we treat it as a LP and solve it, only one variable will be in the solution, and that variable is the one that has the largest coefficient, objective function coefficient by constraint coefficient ratio. So, we sorted the variables in the decreasing order of this ratio, and then we formulated another problem, which is this. In order to simplify the objective function further, we multiplied the objective function by 6, which happens to be the LCM, and then we got this problem. Now, when we solved this problem, we finally obtained a solution with z equal to 8, which is the optimum solution to the integer programming problem, which gave us a solution with x1 equal to 2, x2 equal to 0, x3 equal to 0 and x4 is equal to 1 with z is equal to 8. Now, we have already multiplied the original objective function by 6, therefore, corresponding to that 8, this function when we substitute will give us a value 2 into half, which is 1 plus 0 into half, which is 0, plus 0 into half, which is 0, plus 1 by 3 into 1, which is 1 by 3. So, this would give us 1 and 1 by 3, or this would give us z is equal to 4 by 3. Since we also multiplied this by 6, we have to divide by 6, 8 by 6 would give us the same value of 4 by 3. So, now we have a pattern which satisfies this and hence satisfies this with half a plus half b plus half c plus 1 by 3 d greater than 1, and therefore, this pattern can enter the basis. Now, this pattern is given by, now variable x1 stands for 7 inch and variable x4 stands for 6 inch. Therefore, this pattern has 2 of 7 and 1 of 6 which can enter the basis, and corresponding to this notation that we have used, the entering pattern is now is 0, 0, 2, 1 because it contains 2 of 7 and 1 of 6. So, we have now found out the entering pattern, and therefore, we now next need to find out the leaving pattern. So, this pattern enters the basis and it has to replace one of the 4 existing patterns. So, in order to find out the leaving pattern or the leaving variable, we need to find out p bar j associated with this p j. So, p bar j is always given as p bar j b into p bar j is equal to p j, where p j is the entering pattern. So, let us call p bar j by some a b c d, so that b, which is given here 2 0 0 0 0 2 0 0 0 0 2 0 0 0 0 3 into a b c d is equal to p j, which is 0 0 2 and 1. Now, from this we can compute p bar j is equal to 2a plus 0b plus 0c plus 2d equal to 0. Therefore, a is 0, 0a plus 2b plus 0c plus 0d is 0. Therefore, b is 0. From here, 0 into a plus 0 into b plus 0 into c plus 3 into d is equal to 1. So, d is 1 by 3, and from here 0a plus 0b plus 2c plus 0d is equal to 2. So, c is equal to 1. So, p bar j becomes 0 0 1 and 1 by 3. Now, having found out p bar j, we now have to find out theta. Theta is always the right hand side vector divided by this corresponding element. So, we need to find out theta such that 255.5 minus 0 theta is greater than or equal to 0. So, we do not write it explicitly. 255.5 minus 0 theta is greater than or equal to 0. 150.5 minus 0 theta is greater than or equal to 0. 131.5 minus theta is greater than or equal to 0, and 127.66 minus 1 by 3 theta is greater than or equal to 0. Obviously, these two are not going to be useful in finding out theta because the coefficient is 0. We need to look at only these two inequalities. This would give us theta equal to 131.5. This would give us theta equal to 127.66 into 3, which is much bigger than 131.5. Therefore, this inequality will determine theta, and theta will take a value 131.5, and the third pattern will leave the basis, which means this pattern will leave the basis and it will be replaced by the pattern 0 0 2 1. So, the basis B will change to this, and this column will be replaced by this column. So, the solution, the new solution will be, after we replace this by this one. So, 0 0 2 0 is now going to be replaced by 0 0 2 1. So, this is the change. So, now the basis is updated to this, and we need to find out the solution there. The solution will be 255.5 will remain, 255.5 will remain, 150.5 will remain. This is the binding equation. So, here theta will be 131.5, which will also remain. The last one will become 127.66 minus 1 by 3 theta. So, that will be 127.66 minus 131.5 divided by 3, which is 127.66 minus 4s are 12, 47.166, 4s are 12, 11, 3, 131.5 divided by 3. So, 4s are 12, 11, 3 3s are 9, 8s are 24, 43.833. Now, this on subtraction would give us, if we take this as 43.83, this on subtraction would give us 3, give us 83.83. So, this 127.66 will now change to 83.83. The total has to change. The earlier total was 665.16. Now, the new total becomes 3, 2, 23, 2, 11, 22, 621.33 number of cuts. We can also find out that the decrease from 665.16 to 621.3 is exactly equal to the product of Cj minus Zj and theta, which we are familiar with. So, let us just verify that for a moment. This was the old solution, this is the new solution, 621.33 43.83 was the reduction, which Cj minus Zj in this case was 1 by 3. The reason Cj minus Zj was 1 by 3 is because we have Z is equal to 4 by 3 coming here, and we also have a constraint that this is greater than 1. So, 4 by 3 exceeds 1 by a quantity 1 by 3. Therefore, Cj minus Zj, the actual value is 1 by 3. Theta is 131.5. So, 131.5 divided by 3 is 43.83, which is exactly the gain from 665.16 to 621.33. So, the new basic feasible solution is made up of these 4 patterns 2000, 0200, 0021 and 0003, and it has a total of 621.33 cuts. Now, we need to find out whether this is optimal. So, in order to find out that this is optimal, we need to find out y, which is the value of the dual first. So, yb equal to Cb is the standard equation to get the dual. So, we call y as y1, y2, y3, y4 into the bases 2 0 0 0, 0 2 0 0, 0 0 2 1 and 0 0 0 3 is equal to Cb, which is 1 1 1 and 1. Cb is always 1 because the primal has the objective function of minimize sigma yj. So, whatever be the pattern, the objective function coefficient of that pattern is always 1. Therefore, CB is always 1, 1, 1 and 1. Now, by the very nature of this, it is not very difficult to find out y1, y2, y3, y4 through simplification, therefore, or substitution. So, this would give us 2 y1 plus y2 plus y3 plus y4 is equal to 1, from which y1 is equal to 1 by 2. From the second equation, 0 into y1 plus 2 y2 plus 0 y3 plus 0 y4 is 1. So, we get again 1 by 2. From the fourth equation, 0 y1 plus 0 y2 plus 0 y3 plus 3 y4 is equal to 1. Therefore, y4 is 1 by 3. From the third equation, 0 y1 plus 0 y2, 2 y3 plus y4 is equal to 1. 2 y3 plus 1 by 3 is equal to 1. 2 y3 is 2 by 3. Therefore, y3 is 1 by 3. So, 2 into 1 by 3 plus 1 by 3 is equal to 1. So, this is our dual y. Now, having found the dual y, we now want to find out whether there is an entering pattern. So, if there is an entering pattern, then that pattern will enter and replace one of the existing patterns, and such an entering pattern should satisfy the condition that y into Pj, P bar j, which is equal to y into Pj. So, it should satisfy the condition y Pj is strictly greater than 1. Now, which also means that we have to find out a pattern ABCD such that 9a plus 8b plus 7c plus 6d is less than or equal to 20, which makes the pattern feasible, and it should satisfy the condition y Pj is greater than 1. So, it should satisfy the condition half a plus half b plus 1 by 3 c plus 1 by 3 d is greater than 1. So, it should satisfy the condition half a plus half b plus 1 by 3 c plus 1 by 3 d greater than 1, a b c d greater than or equal to 0 and integer. Now, by the same argument that we did last time, we now convert this into an objective function, and therefore, we rewrite this as half a plus half b plus 1 by 3 c plus 1 by 3 d subject to 9a plus 8b plus 7c plus 6d less than or equal to 20, a b c d greater than or equal to 0 and integer. Exactly as we did in the previous iteration, we find out the ratio between the objective function coefficient and the constraint coefficient. So, this becomes 1 by 18, this becomes 1 by 16, this becomes 1 by 21, 1 by 3 divided by 7 is 1 by 21, and this becomes 1 by 18. Now, we renumber the variables based on the decreasing value of these. So, 1 by 16 is the smallest. So, this becomes variable x1. 1 by 18 is the next smallest. So, we call this as x2 and we can call this as x3. We may also choose to call this as x2 and this as x3, and it does not matter. And 1 by 21 being the smallest will now be called as x4. So, rewriting this, now the problem will become 1 by 2 x1, which comes out of this, 1 by 2 x1 plus 1 by 2 x2 that comes out of this, plus 1 by 3 x3. So, this becomes 1 by 3 x3 and 1 by 3 x4. Now, we realize that this is the variable x1 which corresponds to 8. So, we will have 8 x1. This is the variable x2 that corresponds to 9 inch. So, we will have 9 x2. This is the variable that corresponds to 6 inch. So, we will have 6 x3, and this is the variable that corresponds to 7 inch plus 7 x4 less than or equal to 20. Now, to make this a little more comfortable, we simply multiply the objective function by the LCM, which is 6, to get 3x1 plus 3x2 plus 2x3 plus 2x4 subject to the condition 8x1 plus 9x2 plus 6x3 plus 7x4 less than or equal to 20, xj greater than or equal to 0 and integer. Now, if we are able to find out an x1, x2, x3, x4 that maximizes this subject to this condition and satisfying the integer property, and if the objective function is greater than 6 because we have multiplied it by 6, then such a pattern will have the Cj minus Zj value which is less than 1 and it will enter. So, we need to solve this knapsack problem exactly the way we solved the earlier knapsack problem, and let us do that. Now, the LP optimum will now have variable x1 in the solution because we have already sorted the variables in the decreasing order of Cj by Aj. So, LP optimum will always be from the left. So, the LP optimum to this will be given by x1 is equal to 20 by 8 and z is equal to 60 by 8, which is 7.5. Now, z is equal to 7.5 for this. This is a maximization problem, integer programming. Now, we relax the integer and solve the LP. The LP will be an upper bound to the integer optimum. Therefore, the integer optimum can only be 7 or less. So, we start again drawing this branch and bound tree with the solution x1 is equal to 20 by 8, which is 2.5, and z is equal to 7.5, ZLP is equal to 7.5. Now, since x1 is equal to 2.5, in the integer programming case, x1 can take a value either 0 or 1 or 2 and it cannot take 3. So, we create 3 branches with x1 equal to 0, with x1 equal to 1 and with x1 equal to 2. So, when x1 is equal to 0, it means we are fixing this to 0. So, straight away all the 20 resources are available. This is fixed at 0. So, the first variable now will be in the solution, giving you x2 equal to 20 by 9 and z is equal to 60 by 9. Now, this is 6 point something. So, this can give us if we branch from here, this can give us integer solutions with 6 or less. Now, when we fix x1 is equal to 1, we use up 8 units of this resource by fixing this to 1, which means 12 units of this resource is available. So, this would give us a solution x2 is equal to 12 by 9 and z will be equal to 12 by 9 into 3, 36 by 9, which is 4, plus x1 equal to 1 would give us another 3. So, this would give us z equal to 7. Now, when we fix x1 equal to 2, we use up 16 units of this resource. We have 4 units of this resource available. So, this would give us a solution x2 equal to 4 by 9, z is equal to 12 by 9, plus we have used 2. So, 6 plus 12 by 9, 6 plus 12 by 9 is z is equal to 6 plus 12 by 9, 66 by 9. This would give us 7 and something. So, when we branch from here, if we move down from here, we can get solutions only 6 or less. From here we can get a solution with 7 or less. Here also we can get solution with 7 or less. Now this has the highest value of the lower bound, so we will branch again from this. Now x2 is equal to 4 by 9, so x2 can take only one value, which is x2 equal to 0. That would give us a solution. x1 is equal to 2, x2 is equal to 0. So 16 units have been utilized, 4 units are available. So x3 is equal to 4 by 6, which is 2 by 3. So x3 is equal to 2 by 3. Z is equal to 4 by 3, 2 by 3 into 2, 4 by 3, 4 by 3 plus 6. So Z is equal to 6 plus 4 by 3, which is 28, 22 by 3, which is also 7 plus something. So among all these, the maximum is still here, 7 plus something. This is exactly 7, 7 plus something. So we branch from this. Since x3 is 2 by 3, x3 can only take the value 0, which would leave us with x1 equal to 2, 4 units are available. So x4 will become 4 by 7. So this gives us x4 is equal to 4 by 7, z is equal to 8 by 7. So this would give us z is equal to 6 plus 8 by 7, which is 50 by 7, which is just greater than 7. Now the only feasible solution we can think of in this branching is 2 0 0 0, because this is 4, this can only become 0. This actually gives us z is equal to 6. But then we also have a case here which is possible, 7 is still possible from this. So we have to branch from here. Now here we have x2 is equal to 12 by 9, 12 by 9 is just greater than 1. So x2 can now take two values. This can take x2 equal to 0 and this will become x2 equal to 1. So when x1 equal to 1 and x2 equal to 0, we have x1 equal to 1 and x2 equal to 0. We have 8 units already consumed, 12 units are available. 12 units are available, so x3 will be equal to 2 exactly. So x3 equal to 2 and z is equal to 6 into 2 12, 2 into 2 4, 4 plus 3 7. Now here we have a situation where x1 has taken an integer value of 1, x2 has taken a value 0, x3 has taken a value 2 and x4 will be 0. This is an integer feasible solution with z equal to 7. So we have an integer feasible solution with z equal to 7 to a maximization problem. So this becomes a lower bound. So 7 is a lower bound, but we also understand that if we move from here, only 7 and below are possible. If we move from here down, 6 and below, because this is 6 point something, 6 and below are positive. We have a feasible solution with 7, therefore this solution is optimal. So this solution is optimal with x1 equal to 1 and x3 equal to 2. x2 and x4 are at 0. Now we go back and see that x1 is 8, x1 equal to 1 and x3 equal to 2. So this is 8 inch and x3 is 6 inch. So this is 6 inch. So the entering pattern is 0 1 0 2. This meets the requirement of 20, 8 plus 12 is 20. We now go back and check from here, x1 is equal to 1, so 1 by 2, 1 by 2 plus 2 by 3. So 1 by 2 plus 2 by 3 7 by 6, which is greater than 1, and we got a solution of 7 here. So we have multiplied it by the LCM, which is 6, therefore we get the same 7 by 6. Therefore, this pattern 0 1 0 2 enters the basis. So, we now say entering pattern is equal to 0 1 0 2 from here. Now, this pattern 0 1 0 2 has to replace one of these 4 patterns. Which one we will have to check again. Now, in order to find that out, we have to find out P bar j equal to B inverse P j. B times P bar j equal to P j. So, P bar j equal to B inverse P j, pre multiplying by B we will get B into P bar j is equal to P j. B is known here. So, we write this 2 0 0 0 0 2 0 0 0 0 2 1 0 0 0 3, and let us call P bar j as sum A B C D is equal to P j, which is the entering pattern, which is 0 1 0 2. Now, once again by a process of substitution we can find out A B C D. 2a plus 0b plus 0c plus 0d is equal to 0, which gives us A equal to 0. 0a plus 2b plus 0c plus 0d is equal to 1. So, this gives us b equal to half. 0a plus 0b plus 2c plus 0d is equal to 0. So, this also gives us a 0. 0a plus 0b plus 1c plus 3d equal to 2. C is already 0, 3d is equal to 2. So, d is equal to 2 by 3. So, this is P bar j corresponding to the entering pattern, which is 0, half, 0 and 2 by 3. Now, we use this as well as this to find out the leaving pattern. So, we need to find out theta such that 255.5 minus 0 theta is greater than or equal to 0, 150.5 minus half theta is greater than or equal to 0, 131.5 minus 0 theta is greater than or equal to 0, and 83.83 minus 2 by 3 theta is greater than or equal to 0. So, 83.83 minus 2 by 3 theta is greater than or equal to 0. Now, this would give us a value of 301, theta is equal to 301. This would give us a value of roughly about 120, because this 83.83 into 3 divided by 2 will be roughly of the order of 120. So, this is the variable that will dictate theta. So, we will find out theta corresponding to this. So, theta is now 83.83 into 3 divided by 2. This is 27, 2, 11, 1, 251. So, this will become 125.8 9 125 8 9 5. No, sorry, 3 3s are 9, 8 3s are 24, 2, 11, 251.49 divided by 2. This is actually 251.5, because this is a recurring 0.83333. So, this will become 251.5 divided by 2, which will give us 125.75. give us 125.75. All right. So, we get theta equal to 125.75. The fourth one is the pattern that leaves. So, this is the pattern that leaves, and this pattern is going to be replaced by the pattern 0, 1, 0, 2. So, the new basis will now become the 0, 0, 0, 3, which is the last pattern, will be replaced by 125.75. So, that will be replaced by 0, 1, 0, 2 with theta equal to 125.75. Now, we need to find out the solution corresponding to this basis. Now, 255.5 minus 0 theta, so no change happens to this. This is 150.5 minus half theta, so we have to compute this. So, this is 150.5 minus 125.75 divided by 2. So, 150.5 minus 62.875. So, this is 25625. $87.625 will be the value here. So, this will become 87.625. This will remain as it is, because it was 131.5 minus 0 into theta. Now, theta becomes 125.75 here. So, this is 125.75, and the total now becomes 5, 2 plus 5, 7, 23, 2, 2, 600.375. So, we now have a solution with these 4 patterns coming into the basis with the values that are given here with 600.375. Now, we need to find out whether this is optimal. Now, in order to find out whether this is optimal, we first need to find the value of the dual y, which is given by yb equal to cb. So, let us call y as y1, y2, y3, y4 into 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, 1, 0, 1, 0, 2 is equal to 1, 1, 1, 1, from which y will be equal to 2y1 plus 0y2 plus 0y3 plus 0y4 is 1. So, y1 will be half, 0y1 plus 2y2 plus 0y3 plus 0y4 is equal to 1, y2 will be half. From the fourth one, 0y1 plus 1y2 plus 0y3 plus 2y4 is equal to 1. So, 1y2 will take half. So, 2y4 is equal to half. So, y4 will be 1 by 4, and from the third one 2y3 plus y4 is equal to 1. So, 2y3 is equal to 3 by 4. So, y3 is 3 by 8. So, this is the value of the dual. So, half 3 by 8 and 1 by 4 is the value of the dual. Now, if we want to find out if there is an entering pattern, then such an entering pattern, if it is called Pj, then we need to have ypj is strictly greater than 1. So, if the entering pattern Pj is of the type ABCD, then it should satisfy 9a plus 8b plus 7c plus 6d less than or equal to 20, and it should satisfy ypj greater than 1. So, 1 by 2a plus 1 by 2b plus 3 by 8c plus 1 by 4d greater than 1. So, 3 by 8c plus 1 by 4d greater than 1, a, b, c, d greater than or equal to 0 and integer. Now, we convert this greater than 1 into an objective function and say maximize 1 by 2a plus 1 by 2b plus 3 by 8c plus 1 by 4d such that 9a plus 8b plus 7c plus 6d less than or equal to 20, a, b, c, d greater than or equal to 0 and integer. Now, once again we find out the ratios and sort the variables in the decreasing order of the ratios. So, this becomes 1 by 2 divided by 9 is 1 by 18, 1 by 2 divided by 8 is 1 by 16, 3 by 8 divided by 7 will give us 3 by 56, and 1 by 4 divided by 6 would give us 1 by 24. Now, we have to sort this in the decreasing order of these values. So, this looks just that bit more difficult to sort. So, an easier thing to do instead of directly dividing them is to simply multiply this by a common factor and make this as not dependent on the fractions. So, simply multiply this by the LCM which is 8. So, this will become 4a plus 4b plus 3c plus 2d subject to 9a plus 8b plus 7c plus 6d less than or equal to 20. So, now the coefficients become 4 by 9, 4 by 8, 3 by 7 and 2 by 6. So, roughly 4 by 9 is 4.44, 4 by 8 is 5, 3 by 7 is 4s are 20, 2s are 14, 4.28, and this is 2 by 6 is 3.33. So, the biggest is this. So, this is the variable x1, the next biggest is here which is the variable x2, third biggest is here which is the variable x3, and this is the variable x4. So, we rewrite this problem now as this is the variable x1, so which is corresponding to 8. So, this is half, so you get half x1. This is corresponding to the variable x2, 9 corresponds to the variable x2, so you get half x2. 7 corresponds to the variable x3, so you get 3 by 8, and 7 corresponds to the variable x3. Therefore, 6 corresponds to the variable x4, and you will get 1 by 4 x4. So, we do not need this. So, just to verify once again, 8 corresponds to variable x1. So, we have half and 8, 9 corresponds to variable x2. So, we have 1 by 2 and 9, 7 corresponds to variable x3. So, we get 3 by 8 and 7, 1 by 4 and 6. Now, once again we can multiply by the LCM. So, this will become, because of this change, 7 and this will become 6. So, multiply by the LCM which is 8. So, this becomes 4x1, this becomes 4x2, this becomes 3x3, this becomes 2x4, subject to 8x1 plus 9x2 plus 7x3 plus 6x4 less than or equal to 20, xj greater than or equal to 0 and integer. Now once again we have sorted these in the decreasing order of the ratios. Therefore, x1 will be the only variable in the LP optimum. So the solution will be 20 by 8 with z is equal to 80 by 8, which is 10. 20 by 8 is 80 by 8 give us z equal to 10. So we now start this tree by saying x1 equal to 20 by 8, which is 2.5, and we have z is equal to 10. Now since x1 is equal to 2.5 and z is equal to 10, z equal to 10 is an upper bound to the IP optimum. So based on this, IP optimum can be 10 or below. Now we branch from here, since x1 is 2.5, start with x1 equal to 0, x1 equal to 1 and x1 equal to 2. So when x1 is equal to 0, where x1 equal to 0, we go back here. Now this is 0, so this variable automatically will come into the solution. So this would give us x2 equal to 20 by 9 and z will be equal to 80 by 9. Now 80 by 9 is 8 plus something. So if we branch from here, we can only get a solution with 8 or less. Now x1 equal to 1 would give us, so we use up 8 units, so 12 units are available. So x2 will take a value 12 by 9. So this will be x2 is equal to 12 by 9. Now z will be 48 by 9 plus 4. So this will become 4 plus 48 by 9. 48 by 9 is 5 plus something. So this is 9 plus something. So when we move from here and downwards, we can get a solution with 9 and below. Now x1 equal to 2 would give us 16 units are being used. So 4 units are being available. So this will get a solution x2 equal to 4 by 9, z will be 16 by 9 plus another 8. So this will become 8 plus 16 by 9. So this will be 9 and below. Now out of these, we can either branch from here or we can branch from here. So this is 5 plus 3 by 9, which is 5.33. I am sorry, this is 9.33. So this is a little more than 9.33. So we will branch from here and fix x2 to 0. So when x2 is fixed at 0 and x1 is fixed at 2, the remaining 4 will go to x3. So this will give us x3 is equal to 4 by 7 and z will be equal to 12 by 7. So this will be 8 plus 12 by 7. So once again 9 and below is possible. So we again branch out of this and say x3 is equal to 0. So x1 equal to 2, both of these are 0. x4 will be in the solution with 4 by 6. So x4 is equal to 2 by 3. So the LP solution will be 4 by 3. So 8 plus 4 by 3. But since we have reached all the variables, we should look at an integer solution. So the only integer solution that is possible is 2, 0, 0, 0 with z is equal to 8. Now we have to proceed from here. So this is 12 by 9. So you branch off with x2 equal to 0 and x2 equal to 1. So when you branch with x2 equal to 0, you get this is 1. So this is 0. So 12 units are available. x3 equal to 12 by 7 Z is 36 by 7, 36 by 7 plus 4. So, 4 plus 36 by 7, which is again 9 plus something. So, 9 is possible. Now, let us finish and branch this. Now, since x 3 is equal to 12 by 7, we can now branch as x 3 equal to 0 and x 3 equal to 1. Now, x 1 equal to 1, these two are 0. So, 12 units are available, x 4 will take 2. So, this will take x 4 equal to 2 and z will be equal to 4 plus 4, which is 8. So, we get a pattern x 1 is 1, 0, 0, 2 with z equal to 8. Now, when we proceed from here, x 1 equal to 1, x 3 equal to 1, 15 units are being used. So, x 4 has 5 by 6. We are not worried about z because the only integer solution possible is 1 0 1 0 with z equal to 4 plus 3 7. Now, we also need to branch from here. This is x 1 equal to 1 and x 2 equal to 1, which means we have used up 9 plus 8 17 with z equal to 8. None of these can get anywhere near 1. So, in the integer solution both of these will be 0. The only integer solution possible will be 1 1 0 0. Proceed further, x 1 equal to 1, x 2 equal to 1, use as 17 units of the resource, 3 units are available. So, x 3 will be 3 by 7 and z will be 8 plus 9 by 7, which is slightly greater than 9. So, we can still branch on this. So, this would give us x 3 equal to 0, the only possibility, and therefore, now when we branch on x 3 equal to 0, 8 plus 9 17, 3 units are available. So, x 4 will become half, this will become 1, but the only integer solution possible will be 1 1 0 0 with z equal to 8. Now, if we proceed from here also 80 by 9, we can only get integer solutions with 8 or less than that. So, either way if we move, we already have solutions with 8. So, we can fathom this, we need not proceed out of this, we have feasible solutions with 8. Therefore, we may take 8 as the optimum for this. But when 8 is the optimum for this, we have already got this objective function from this by multiplying this by 8. So, z equal to 8 here implies z equal to 1 here. So, the optimum solution does not give us a pattern with strictly greater than 1, it gives a pattern which is exactly equal to 1. So, when we are unable to find a pattern with strictly greater than 1, when we solve the knapsack problem, we say that the optimum solution is reached, because we are unable to find out an entering pattern. So, there is no entering pattern, and therefore, this solution, the present solution is optimal, which has 2000 255.5 sheets, 0200 87.625 sheets, 0021 131.5 sheets, and 0102 with 125.75, giving us 600.375 sheets at the optimum. So, this is how we solve the cutting stock, one dimensional cutting stock problem by using the procedure of column generation, and the column generation comes by solving a sub problem. What we actually did is an algorithm which is pretty much like simplex, because we have started with a basic feasible solution to the primal, we obtained the solution to the dual, and then we evaluated whether all the corresponding duals are feasible by finding out if there is a possible entering pattern. So, it is very much like simplex, where we start with a basic feasible solution to the primal, check for dual feasibility, which means check for optimality of the primal, and if it is optimal, then take that solution as the final solution, which is what we did. The only difference in this case was we did not explicitly store all possible coefficients or all possible variables or all possible patterns. Instead, every time we had a basic feasible solution to the primal, and to check whether the primal is optimal, we searched and found out is there an entering pattern. If there is an entering pattern, we identified the entering pattern and then we brought it in. How did we generate the entering pattern? We generated the entering pattern by solving a single constrained knapsack problem, which is given here, a one constrained knapsack problem, which by itself is an integer programming problem. We are going to see much later that integer programming is actually hard. It is not as comfortable as solving linear programming problems. Nevertheless, the branch and bound procedure that we described here makes the integer programming solvable very quickly, particularly when we write a computer program and proceed. So, for large sized problems, large number of variables, perhaps a large number of individual patterns that we have here, then it is the procedure by which every time to find out an entering variable, you solve a sub problem, and the sub problem turns out to be a single constrained knapsack problem, which is solved using the branch and bound procedure, and then we generate the entering column. So, that is called column generation. We do not store all the columns, we generate the column in every iteration depending upon whether such a column exists. So, in this one dimensional cutting stock problem, we have now learnt the idea of a column generation. Invariably, column generation would involve solving a sub problem, and in this case it was a knapsack problem. Even though integer programming was hard, it is still doable. Therefore, one dimensional cutting stock problems are solved using a combination of column generation and correspondingly solving the knapsack problems. In the next lecture, we will look at the decomposition algorithm to solve large linear programming problems.